In the previous lecture, we covered the adjacency list, a widely used way of representing graphs. In addition to the adjacency list, we have another way of doing so. It's the one we will see in this lecture, the adjacency matrix. The adjacency matrix is a square matrix of size length of v times length of v, where matrix of ij says if yes or no there is an edge from I to j. 1 if there is an edge from I to j, 0 otherwise. For example, if matrix of 1, 5 is 1, it means that there is an edge from 1 to 5, and 0 means that there isn't. Quite simple to understand, I think. Here is an example. We can see that matrix of 1, 5 is 1, so there is an edge from 1 to 5 as you can see. But matrix of 4, 7 is 0, then there is no edge from 4 to 7 as you can see. For an undirected graph, edges are bidirectional, so if matrix of ij is 1, matrix of ji will also be 1, and if matrix of ij is 0, matrix of ji is also 0. This is why with undirected graphs, we get a symmetric adjacency matrix. And for weighted graphs, if there is an edge from I to j, we put the weight in that cell, else we put 0 or infinity. Infinity is preferred in cases where the weight can be 0, to avoid ambiguity. Here is an example of a weighted graph and its adjacency matrix. You can see that in cells where there is an edge between the vertex of that row and the vertex of that column, we don't just put 1, we put the weight. And when there isn't, we can put infinity, to say that there is no edge. For the implementation, we will use a matrix of size length of v times length of v, an array of arrays, all having the same size. At the beginning, the matrix is empty. We will add rows and columns either when we add a vertex or when we initialize it by giving it a set of vertices and a set of edges. First operation, add vertex. To add a vertex, we have to add a new row and a new column to welcome the new vertex. And here, it depends on the implementation. If the adjacency matrix is static, we have to create a new one from scratch whose the size is the size of the old matrix plus 1, and we copy values of the old matrix. And if it's dynamic, like in what we did, we traverse rows to add a new cell at the end of each one of them. Then, we add a new row at the bottom. In code, we traverse rows, we append a 0 to each one of them to gradually create the column. Then, we append a new row that has the same size as the first one, for example. For removing a vertex, we need to remove the row and the column of that vertex. For example, here if we want to remove vertex 2, we remove row and column 2. And to do so, we swap row 2 with the last row, we pop to remove the last row, and same logic for the column. We swap it with the last column and we pop from each row to remove the last column. In code, we swap the row I with the last row, we pop from the matrix to remove the last row, and for the column, for each row, we swap the element I with the last column and we pop. That's it. After the loop, we will have removed the column we wanted to remove. Next operation, adding an edge. Adding an edge in an adjacency matrix is really easy. We just need to put one in the right cell. We want to add an edge from the vertex u to the vertex v, so we put one in the cell at row u at column v. For example, if we want to add an edge from vertex 2 to vertex 3, we put one in edge matrix of 2, 3. In code, we just put one in edge mat of u, v. And if the graph is undirected, we need to also add an edge from v to u, so we also put one in edge mat of v, u. And for removing an edge, same logic but we put 0 instead of 1. That's it. And for checking if there is an edge from u to v, we just check if the cell edge mat of u, v is equal to 1. Next operation, traversing neighbors. Neighbors of a vertex U are vertices V with which there is an edge between U and V. And to find them, we traverse the row U in the adjacency matrix and check cells where there is a 1. For example, in this matrix, in the row 4, cells where there is a 1 are 0, 1, and 5. So neighbors of the vertex 4 are 0, 1, and 5, as you can see in the graph. In code, we traverse vertices V, and if edgemat of UV is 1, then V is a neighbor. We perform the action we want, for example, printing it here. Last operation, building the adjacency matrix. We have a set of vertices V and a set of edges E, and we want to build the adjacency matrix. We know that an adjacency matrix has a size of length of V times length of V, one row and one column for each vertex. This is why we create a matrix of length of V rows and length of V columns. Cells are initially at 0 because we didn't add edges yet, we just created the vertices. Next step, we traverse the edges to fill the cells. For each edge, we have the source and the destination. So we put 1 in the cell at row source at column destination. It means that we have an edge from source to destination. If the graph is undirected, we also put 1 in the opposite cell. We put 1 from destination to source. We put 1 in edgemat of destination source. Now we've seen how to implement an adjacency matrix and different operations, but we missed something important. To access vertex 3 in the adjacency matrix, we go to row 3. But what if the vertex was a string, for example? How would it work in the adjacency matrix? The answer is that, to allow vertices to be something other than integers from 0 to n-1, indices, we need a hash table that stores each vertex and the index of its row, column, to be able to access it. For example, here we have 6 vertices A, B, C, D, F, so we create a matrix of size 6 by 6. Now we have 6 indexes 0, 1, 2, 3, 4, 5. We can, for example, decide to give index 0 to A, index 1 to B, index 2 to C, index 3 to D, index 4 to E, and index 5 to F. By doing so, if we want to access the row with the vertex C, for example, we check the map, we find 2, so we go to row 2. Little example, to add an edge from A to E, we check the index of A, which is 0, the index of E, which is 4, and we put 1 in the cell edgemat of 0, 4. We fix the problem. Now we know about the adjacency list, the adjacency matrix, but one question remains. If we want to implement a graph, what implementation should we choose? To answer this question, we will compare space usage and time complexity of operations of each one of them. This is what we will do in the next lecture.